Let's now take a look at a molecule where the central atom has 5 groups of electrons sticking out of it. So the steric number is 5. An example of this would be PCl5. Okay, if you were to draw the Lewis structure of PCl5, you'd do something like this. Okay, phosphorus, okay, contributes 5 valence electrons. It's right under nitrogen in your periodic table, so group 5A. Each chlorine contributes 7. It's a halogen. It's group 7A. There's 5 chlorines. We're doing PCl5, so times 5. That gives you 35. So PCl5 would have 40 valence electrons, and so you're going to, if you surround your phosphorus by chlorines, 5 chlorines. Remember, phosphorus is in the third row, so it can have an expanded octet. In this case, it actually has 10 electrons around it rather than 8. So it doesn't have, has more than an octet. So that's 2, 4, 6, 8, 10. So each chlorine has an octet, so it needs, each chlorine needs 3 lone pairs, 2, 4, 6, and the bonding pair makes 8. So this chlorine needs 3 more. This chlorine needs 3 more, this chlorine needs 3 more, and this chlorine here needs 3 more. And so you have 5 chlorines, each one would have an octet, so 5 times 8, that takes care of 40 valence electrons. You've got all the electrons covered. And if you look at your formal charge, each chlorine by itself would have 7. It appears to own 6. Plus half of the pair, so 7, 7 minus 7, formal charge on the chlorines would be 0. Phosphorus by itself would have 5, and you can see it's making 5 bonding pairs here, so half of 5 pairs would be 5 electrons, 5 minus 5, 0 formal charge. So this is the perfect Lewis structure for PCl5. So this is what the molecule would look like. Your phosphorus is going to be right here in the middle. You have chlorine, 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 chlorine. That's how the chlorines would be arranged. Okay? This arrangement is called a trigonal bipyramidal arrangement. Trigonal because it's like, and bipyramidal. Imagine you have 2 pyramids here with a triangular base. So here's your triangular base right here. These 3 chlorines here form what's called the base of the pyramid. You have one pyramid pointing upward, and your other pyramid is pointing downward. Okay? So 2 trigonal pyramids, one pointing up, one pointing down. So it's a trigonal bipyramidal structure. So what you have here, your center, your phosphorus, you say, is a trigonal, your phosphorus is a trigonal bipyramidal center. Now, let's look at the angles. Okay, so these 3 chlorines over here at the base of the pyramid, okay, imagine those are at the equator of the Earth. The other 2 chlorines, this one right here, imagine this chlorine as at the North Pole, okay, and this other chlorine is at the South Pole of the Earth. So if imagine this as the 3 chlorines, you can refer to the 3 chlorines as your equatorial groups, and the 2 chlorines that are at the North Pole and the South Pole are called your axial groups. Okay, so your equatorial groups, the angle between any pair of your equatorial groups is 120 degrees. So it's like if you're looking at it from the top, you'll see the equatorial groups would look like that. So so the North Pole, one axial group is going to be sticking towards you, and the other axial group is going to be sticking downward away from you, sticking away from you. Okay, so this would be your equatorial groups would be 120 degrees apart. So this angle right here between this and that's 120 degrees. The angle between this and that would be 120 degrees. So equatorial positions are 120 degrees apart. Each axial group is perpendicular to the plane of the equatorial group. So that's the axial groups are 90 degrees from the equatorial groups. Okay? The angle between the two axial groups, since they're sticking in opposite direction, would be 180 degrees. So axial groups are 180 degrees apart, and they're perpendicular to the equatorial groups. So we say in this case, your phosphorus right here is a trigonal bipyramidal center. The shape of the molecule is also trigonal bipyramidal. So this is type AX5. There's 5 groups sticking out of your phosphorus, and there's an atom at the end of each of those 5 groups. There's no lone pair. Now, what happens if one of those groups happens to be a lone pair and you don't have an atom there? So let's take a look at the situation here. You have a steric number of still of 5, but one of those groups happens to be a lone pair. That's the case when you have SF4. Let's figure out SF4 first, the lowest structure. Okay, SF4. Sulfur contributes 6. Fluorine, okay, because it's in column 6 of your periodic table. Fluorine contributes 7 valence electrons. There's 4 of them, so 7 times 4 is 28. So SF4 will have a total of 34 valence electrons. Okay, so if you surround your sulfur with 4 fluorine atoms, and then give each fluorine atom an octet, so each fluorine atom already has one bonding pair, so each one just needs 3 lone pairs. 1, 2, 3. 1, 2, 3. Okay, let's count what we have so far. You have 4 fluorines, each one with an octet, so 4 times 8. We're only showing 32 valence electrons here. But SF4 has 34 valence electrons. So that means you need 1 more lone pair to make 34, and so that extra lone pair goes on the sulfur. So the sulfur, we say, has 1, 2, 3, 4, 5 groups sticking out of it. 4 of those groups are single bonds. The 5th group is a lone pair. Okay, so this is AX4E. 4 groups with an atom at the other side, and then you have a lone pair. Well, since a lone pair is much bulkier than the single bonds, it will try to find a position that is farther away from the other groups, and the preferred positions of lone pairs would be the equatorial positions. Remember, equatorial positions are 120 degrees away from each other, whereas an axial position is 90 degrees from 3 equatorial positions. So if one of these equatorial positions is taken by a lone pair, okay, so imagine this atom is not there anymore. You only have 4 fluorine atoms, right? And you have your sulfur right there. Okay, there's no atom here. That's just a lone pair. So there's that lone pair right there, the missing atom. Here's your equatorial position. You can see this thing looks like a seesaw. So here's the fulcrum right here where the sulfur is, and here's Jack, and here's Jill over here. Okay, so you say that SF4 is type AX4E. The sulfur is still a trigonal bipyramidal center because there are 5 groups sticking out of it. But the shape of the molecule itself, the SF4 molecule, we say, has a seesaw shape. Okay? Now, what if you have 5 groups of electrons sticking out? Then, and you have a steric number, but 2 of those happen to be lone pairs. So 5 groups, steric number is still 5, but 2 of those groups happen to be lone pairs. Okay, those 2 groups will take equatorial positions. Okay, so let's imagine BRF3 is going to be like this. Bromine right here in the middle, 3 fluorines. Okay, the preferred position for the lone pair would be equatorial. So this position is gone, that position is gone. So the fluorines take 1 of the equatorial positions and 2 of the axial positions. Okay, so this is what you get. And so this bromine right here has a lone pair over here and a lone pair over there. All right. So the shape of the molecule, we say, is T-shape. Okay? But bromine itself, because there are 5 groups sticking out of it, is still a trigonal bipyramidal center. So this is type AX3. There's 3 ligands or 3 atoms attached to the bromine. By the way, another word for the word for X here is ligand, atoms that are attached to the central atom. Okay? And there's 2 lone pairs. So this is type AX3E2. Now, how did we figure out that there are 5 groups in BRF3? Let's go ahead and do that. Bromine by itself should have 7, so it contributes 7. Fluorine is also a halogen, group 7A, so it contributes 7. There's 3 of them, so that gives you 21. So BRF3 needs 28 valence electrons. Okay, so how do you arrange those? Distribute those. So you have BRF, 3 BRF bonds. Then each fluorine gets 3 lone pairs because each one already has a bonding pair, so that would give it an octet. This fluorine gets another 3 lone pairs to give it an octet. This fluorine down here needs 3 lone pairs to give it an octet. So you have 3 octets around the bromine, so that's 8 times 3, that's only 24 valence electrons, but we have 28 valence electrons, so you need 2 more pairs of valence electrons, so you need 2 lone pairs on the bromine. So you have 1, 2 lone pairs, okay, 3, 4, 5, so you have 3 single bonds and 2 lone pairs, so that's a total of 5 groups sticking out of your bromine atoms. So your bromine, we say, is a trigonal bipyramidal center. Now, ICl2 minus, you can show that this is also going to be have a steric number of 5. Okay, your iodine is going to have 3 lone pairs and 2 Cl bonds, ICl bonds, and this thing is going to have a charge of -1. So those 3 lone pairs are going to take up the equatorial positions, and so the chlorine will be at the axial positions, and the iodine is going to be in the middle. So the shape of the molecule is going to be, in this case, linear. 3 atoms on a straight line. The shape of the molecule, actually the ion, because it's an ion, the shape of the ion is linear, even though the central atom itself is a trigonal bipyramidal center. So this is type AX2E. There's 2 atoms attached to the central atom. By the way, another term for the number of atoms attached to the center is coordination number. So the coordination number of iodine here is 2. Okay, so that's your coordination number right there.